Always too loud. Good morning, everybody. We have been talking about cyclohexanes and how crazy stable and uncomfortable they are to draw. What I want to do is talk about adding a big group on there and flipping it back and forth, comparing the relative stability, and then we're going to put two groups on there and flip it back and forth and compare the relative stability. So let's start out with section 4.7, which is conformations of monosubstituted cyclohexanes. Okay, so what I'm going to do is draw a cyclohexane that has a methyl group on it. I'm going to put that methyl group on a wedge, which means it's going to be above the ring. So whenever you draw two chair flips, what I recommend you do is draw the two chairs blank next to each other, because you're going to get credit just for knowing how to draw a chair, and showing the two chair forms next to each other will be kind of the first step of that. So I'm going to arbitrarily draw the negative slope chair first. And then in the next structure, I'm going to draw the positively sloped chair. And again, I'm just using these words to try and separate out each chair flip. These are two chair flips of each other. And what I'm going to do is just choose this rightmost carbon to put the methyl group on. Whatever carbon you choose is fine, but it will change the nature of if it's axial or equatorial. So I have a methyl group that's on a wedge. I am arbitrarily picking this carbon to draw it here. So that means this carbon, the methyl group, needs to be above the ring. Is above the ring at this position axial or equatorial? Axial. So I would draw the methyl group facing straight up. When we have things like methyl groups in axial positions or big groups in axial positions, they are closer to the rest of the ring. And I didn't bring my model kit today, and I totally should have, because it would have been good. But when I bring that methyl group into an axial position, it is running into these other carbons over here. And we show that sometimes by showing just the hydrogens, but it's the methyl group, the carbons, and the hydrogens. What this is called is, if this is position 1, then 3 carbons away, you're going to find another axial position that's facing up. So this is axial up at position 1. This is axial up at position 3. And so we call that an axial interaction. Well, there's 2 of these, 1, 2, 3, or 1, 2, 3. When we put a big group in an axial position like that, we call that a 1, 3 diaxial interaction. Those are bad. Right? So when you put a big group in an axial position, it incurs a penalty. In this case, if you have a CH3 here, it costs 7.6 kilojoules per mole more in energy. I'm not going to write that number down and have you memorize it, but actually, I'll put it on here because I'm going to show you later on. You don't need to know these numbers. But this is 7.6 kilojoules per mole higher in energy. Or let's say 7.6 kilojoules per mole less stable. When we do our chair flip, this carbon on the far right is still going to be this carbon on the far right over here. The methyl group is still above the ring. Is above the ring at this position axial or equatorial? Equatorial. So what's going to happen is our axial methyl group is going to fold into an equatorial methyl group. There is no energy penalty for having the methyl group be there's no energy penalty as far as the axial concerns as far as the axial interactions are concerned. when the methyl group is in the equatorial position. So there's going to be an equilibrium set up between these two molecules, but it is going to heavily favor the methyl group in the equatorial position. Only a little bit, it's going to be back in the axial position on this side. This is the most stable. And this situation is exacerbated as the groups get bigger and bigger and bigger. Sorry, before I'm moving quick here. That makes sense? If you have a big group on a cyclohexane, you want it to be in an equatorial position. Axial, if this is my ring, axial makes it run into the ring a lot more than equatorial. Equatorial, the big group's kind of sticking out to the side. Axial, it's closer to all the other guts of the ring. And my ring is structured here, so I can't really do it, but spread out the density, crush it. The steric strain increases. With substituent size. Since something a little more impactful about red. If I put an X group up here, like I said earlier, if the X equals a methyl, that's going to cost us 7.6 kilojoules per mole. That number, by the way, comes from the A value. So when we talked about Newman projections, and we said that it costs 3.8 kilojoules per mole to put a methyl group next to another, to a hydrogen, that is 3.8. Well, there's two of those, right? So 3.8 times 2 is 7.6. I don't need you to know where these come from, or you don't have to know where these come from, but if you ever want to look these up, you can use the A values to predict what these structures are going to cost you. If that goes from a methyl to an isopropyl, it costs 9.2. And if we take that up to a T-butyl, it's 22.8. You can see what's happening when I go from methyl to isopropyl to T-butyl. We are exponentially increasing the amount of energy that we have to pay to put these big groups into axial positions. If you have a T-butyl group on a cyclohexane, get it off the axial position, right? If the T-butyl group is facing straight up, it takes up way too much space. So we want to tilt it away and make it equatorial as quickly as possible, because we pay a huge penalty to put big groups in that position. Basically, what I'm saying is the relationship in this equilibrium gets more and more lopsided as this group gets bigger. Right? So when there's a methyl group up here, it costs 7.6 kilojoules per mole. And so it's not great, but it can exist. If this were a T-butyl group, this would almost not be in equilibrium at all. It would be all of this conformer, right? Because the T-butyl group is so big that it's going to just stay in the equatorial conformation. Yeah? Sure. No, we are not. We have questions. What are they? I'm feeling a bit out of sorts today, and I think you guys are picking up on it, and or this is really complicated, and or both. Both. You got to ask questions if you want to slow me down. Otherwise, I'm going to just keep going. Yes, ma'am.
The one green bag, why didn't you count like the hydrogen one?
Because it's really this carbon that it's running into. Because remember what's happening is this group, this carbon is puckered up. Well, this carbon's puckered up as well. And so what's happening is I've got a carbon 3 carbons away. So where my head is, my head's the methyl group, right? Got a giant head. 3 carbons away, there's a carbon that's puckered up. And so my head is running into that carbon, right? So at the 3rd position, I'm running into the other carbon that has an axial group. It's just another way of saying that. I don't run into the 2nd carbon because its axial position is pointed away from me, right? So if I'm big, my next carbon neighbor is down this way. So I'm not really running into him. The carbon neighbor after him, though, is coming up this way. So he is kind of in my direct line of sight. So my bigness is running into a carbon 3 carbons away, not right next door. Okay. You guys love mono-substituted cyclohexanes. We should talk about di-substituted cyclohexanes. Part of the reason I'm also like super distracted up here is I have 18 text messages right now. And if the world's not on fire, someone's gonna be in trouble. My son's 5th birthday today, so we're organizing all that. Guys, he's so cute. He woke up this morning and I was like, hey buddy, happy birthday to you. And he goes, no, save it. And then we gave him a special donut. It was like shaped like a unicorn and had little like unicorn droppings as the donut holes next to it. He like loved it. And then we were walking out the door and he was like, we forgot to sing happy birthday. So we had to run back into the bathroom and sing happy birthday with my wife and then get back over here. So I'm distracted. Let's talk about conformations of di-substituted cyclohexanes. A tale of 2 di-substituted cyclohexanes. What I'm going to do each time is I'm going to draw for you the top-down version so that we can kind of map it out onto the chair forms. So, and that's also I would give you the top-down version like this. Let's say here is a cyclohexane. Some of us got real close. We're like this close to just nailing naming. And I was trying to give you the benefit of the doubt. So if you see on your quiz where I wrote careful on a lot of quizzes here, where you're like, this close, but it was like the tiniest little thing. Technically, I should take off a point for that, but I didn't feel right giving you half credit for this tiny little mistake. But just be aware that as we continue to do more of this, I gotta hold you to account at some point, right? So what is the name? What is the actual specific name of this molecule? There we go. I was about to say cis. All right, so the 2 methyl groups are on the same side. So this is a cis. That's not how you write cis. Cis. 1, 2. Dimethyl. This would all still be one word, but I need space, so I'm going to finish it down here, but dimethyl cyclohexane. I want to draw 2 chair forms of cis 1,2 dimethyl cyclohexane. Again, what I highly recommend you do when you're doing this analysis, and remember, we have to draw the chair forms because I'm trying to figure out, are they axial or are they equatorial? And that is impossible to tell from this structure. This structure cannot convey axial versus equatorial. It depends on where you draw them. So the thing I recommend you always do when you're drawing 2 chair forms is draw them blank and then fill them out like a worksheet. Let's draw 2 chair forms. I tend to draw the negative slope first. That is just my own personal preference. It is arbitrary. And where you put the carbons are arbitrary. Where you put one of the carbons is arbitrary, I guess. Are we getting good at drawing chair forms? Yeah? Yeah? Right, some of you are like, baller, got my tattoo all ready to go. And some of you are going, If you're going, you keep drawing these things on everything you find. Every napkin, every envelope, if you're tagging a building, maybe don't do that, but if you do, cyclohexane would be pretty sweet. I'm not encouraging people to graffiti. Draw these on everything, so you're used to putting these out. Drawing just 2 chair forms with nothing on it will get you points on quizzes and on exams, and drawing a good chair form is its own special art. I am going to put these 2 methyl groups here on the end. I am arbitrarily going to put one of them here and one of them here. Now, when I put a methyl group here, either one is on a wedge. So if I put it up on this carbon, is it axial or equatorial? Axial. This carbon's up position is axial. Now, when I plant my flag here of this carbon, now I have to start following my own rule. I'm going to put the next carbon down here. I just as easily could have put it over here. And when I have you draw chair forms, you can put the carbons wherever you want. What you cannot do is turn a 1,2 dimethyl cyclohexane into a 1,4 dimethyl cyclohexane, right? So you can't break that rule. But once I plant a methyl group here, I can either use this one or that one. I'm going to use this one because it's a little more open, easier to draw on. At this position, I need to draw another methyl group that's on a wedge. Do I draw this up position, axial or equatorial? Axial would be straight down. So the other one, equatorial. Both of these methyl groups are on a wedge. Both of these methyl groups are above the ring. One's axial, one's equatorial.
So is that, like, I guess my struggle is like knowing like
Which one to choose?
Yeah.
So that's why you always want to draw 2 chair forms, because you're going to arbitrarily put the carbons somewhere. And as long as you keep them on those same carbons in your next structure, you will be able to tell the difference between those 2. So if I started here, I would have this one be equatorial up and that one be axial up. Well, my structure would still have one axial, one equatorial. They would just be in different location from the place I originally drew it. Now, the key to not drive yourself crazy here, and to answer Miguel's question, if this is carbon 1 and that's carbon 2, that is carbon 1, that is carbon 2, and you need to keep those the same. If I rotate this around in my next chair form, I will drive myself nuts, because carbon 1 in an axial position is going to turn into an equatorial position. Carbon 2, which was equatorial, is going to become axial. Which one of these chair forms is more stable? They are equal. There is no difference. So true equilibrium between these 2. It's flipping back and forth, but as far as the molecule is concerned, doesn't matter. It's always going to have one axial methyl group and one equatorial methyl group, no matter what it does. Which isn't very satisfying as an example, is it? Don't worry, I have another one. Don't draw this, but to Miguel's question of where do I start, right? The thing I think that makes people nervous about this subject, and again, everything I'm gonna draw in green is just another way you could do this. If I just gave you this and said, draw cis 1,2 dimethyl cyclohexane in 2 chair forms and tell me which one's more stable, you would draw 2 blank chair forms. If you were maybe 2 good chair forms. If you were smart, and you're all smart, so you're all going to draw me 2 blank chair forms, so you know I know what a chair flip is, and then you're going to arbitrarily pick where you want one of those methyl groups to go. Miguel, give me a carbon. Which one do we want? Left, right, back, front? Bottom left. Okay, so Miguel is picking this carbon to put one of those methyl groups. Either one of them is going to be on a wedge, so it doesn't matter. I can choose whichever one I want to be carbon 1 here. So I'm going to put, this has to be above the ring. Above the ring right here is a equatorial or axial? Equatorial. So that's the part where you have to be able to see on this. If the carbon's puckered down, the up position is equatorial. All right, Miguel, do you want me to go with the next methyl group here or here? It has to be on one of these two because it's a 1-2, right? Back one, front one. Up, okay. The carbon that is puckered up needs to have a methyl group facing up. Is that axial or equatorial at this position? That's axial. So Miguel's structure that he just drew for us is different than mine, but they are the same as far as this molecule is concerned. One axial methyl, one equatorial methyl. It's the same molecule, just rotated around to a different position. If I did my chair flip over here, that is going to turn into equatorial, this one, equatorial up. This one goes to axial up. One axial, one axial, one equatorial, one equatorial. The only difference is my carbon 1 and 2 were there. Your carbons 1 and 2 are here and here. So there's lots of permutations of how this thing can be drawn. It's a ring, right? So you can rotate it. Draw the chair forms first, and then keep your carbons in the same orientation. Do not draw your CH3s over here and then do a chair flip. Thank you, Warren. And then do a chair flip and put your CH3s over here. It'll drive you nuts, right? Don't put them on the left-hand side, flip the chair, and then rotate it. You're doing like that little follow the ball in a cup game. Anybody ever done that on the street? It's always like a shady character in a big town that's like, follow the cup. And you're like, I don't want to talk to you. And you move the cup around. The more motion you, I don't know what I'm talking about. The more motion you give a molecule, the more you have to account for that as you're flipping the molecule around. If you put the methyl group number 1 here, keep number 1 over there. Am I beating this to death? Or are we confused? Or are we sleepy? Or is it Friday? I am beating it to death and we're confused. Good. Okay. Let's talk about molecules where it's different. So that was cis 1,2-dimethyl cyclohexane. What if we had the other one? The name of this molecule. Trans 1,2-dimethyl cyclohexane. First thing I'm going to do is draw 2 blank chair forms. Now I need to pick a carbon where this is going to go. So who wants to try, instead of me just picking one, because I think that's part of this, is we got to figure out where we want to plant a flag, where we want to put a carbon. Who wants to drive and draw these structures with me? I'll help. But I'm going to show you how arbitrary it can be. Anybody brave? Gracie, you look brave back there. Gracie's feeling brave. Where should I put one of these methyl groups?
Middle.
In the middle. In the back or the front? The back. That one? Yeah, let's do it. Okay. Do you want me to use the wedge carbon here or the dash carbon here? Let's do the dash. I love it. Okay. So this carbon is going to be our dashed methyl group. This carbon, putting a methyl group below the ring, is axial or equatorial? Is equatorial. We wanted a dash carbon, so we said we're going to put that below the ring. The below the ring position at this carbon that we arbitrarily chose is equatorial. Because if I would have drawn it this way, it'd be above the ring. Axial up, equatorial down. Okay. I can put the next carbon here or here. Do you want me to put it on the left or the right, Gracie? On the right, okay. This carbon is puckered down. I need to, so I'm going to put some random numbers up here just to keep track of it. We're going to call this carbon number 1, We're gonna call that carbon number 2. Because we put number 1 here, I'll put number 2 over there. Number 2 has a carbon on a wedge. That means that that methyl group is above the ring. At this position is above the ring, axial or equatorial. The carbon's puckered down, so it's axial down, which means the up position is equatorial. Go through that one more time. The carbon number 1 that we arbitrarily picked on this structure, which, by the way, and this is no fault to Gracie or anybody else in here, these back carbons are a little messy to label, right? So I typically like to use the outer edges just because it gets kind of more crowded in here. But any carbon you pick, you can make these structures work. Carbon number 1, which we arbitrarily chose was this, was on a dash. The methyl group was on a dash. That means that that methyl group is below the ring. The below the ring position here is equatorial because the carbon's puckered up, the methyl group is equatorial down. At carbon 2, we are given a wedge. That means that that methyl group is above the ring. So we come over to this position and say, if I wanted to put something above the ring on this carbon, does it have to be axial or equatorial? Carbon is puckered down, which means it's axial down, so equatorial up. When we do the chair flip, you got to recognize that carbon 1 is here. Move this out of the way. That's carbon 1. That's carbon 2. And that's why I think these middle carbons are a little more confusing, because some people like to say, well, this carbon 1 should be that over here. But keep in mind, the end carbons, the leftmost carbon, I'll put a little dot on it, is that carbon. The carbon on the rightmost is that carbon. So those will always stay the same. The flippers just move up and down, but leftmost and rightmost stay the same. Carbon 1 was equatorial down. Carbon 1 is now going to be axial down. Carbon 2 was equatorial up. Carbon 2 is now axial up. Which one of these two structures is more stable? That guy. The other right. That's right. That's correct. Why is this molecule the most stable? It's most stable because the CH3s are equatorial. That means the equilibrium is going to heavily lie this way and not much go back that way. The rule of thumb here is that cyclohexanes are most stable when bulky groups are in equatorial positions. Why? Because putting them in axial positions makes them run into everything else. So this methyl group runs into, maybe don't draw this on your structure because it's about to make it really messy in here. 1, 2, 3, 1, 2, 3. This methyl group runs into that hydrogen. This is called steric hindrance. This methyl group runs into that hydrogen at that axial position and this hydrogen at that axial position. Same thing down here. This methyl group runs into that hydrogen and that hydrogen. So we have these interactions, these diaxial interactions from the methyl groups being in the axial position. We alleviate that when the methyl groups are in the equatorial position. I have, see how dramatic I can make this. I am a cyclohexane, and pretend I'm zigzag, but here's my ring. My chest and my head are some big group in an axial position. If I have a big group that's in an equatorial position leaning away from me, we're not really running into each other. But if I put that big group on the end, so 1, 4, if I put that big group on the end, my head is now much closer to this. So I'm running into that group because it is an axial interaction. In the equatorial position, I alleviate that. If I were to do that with my head, it'd be like equatorial, right? We're just taking all the bulk and saying, there's a lot of atoms in here. Let's put you kind of out of the way. Equatorial is like, why don't we sit down for a minute over here in the corner, not be like all up in everybody's Kool-Aid. Now, let's try one real quick. I mean, not real quick, but expeditiously. I want you to draw 2 chair forms. Of that molecule. Right? You like how it was like, here's really simple with like 2 methyl groups, it's no problem. And here's a whole bunch of stuff. You can do it. Draw 2 chair forms. After you draw your 2 chair forms, put your groups on there, and I want you to label them axial or equatorial. Then I want you to take a look at both of those chair forms, and I want you to circle the one that is more stable. Okay. I'm gonna use the N carbons here. When you have a 1,4 substitution, it's a very good idea to make the left and the right 1 and 4. Doesn't matter which one, but 1 and 4 on the ends is a very good idea because they're just easier, right? The leftmost carbon is still the leftmost carbon. It's just easier to track your eye. If you didn't do that, you can still get the right answer, but you're making it harder on yourself, especially when you're drawing these big freaking T-butyl groups. So I'm going to put the T-butyl group either on the left or the right. Where should I put it? You did yours on the left. I like Miguel. So we are going to go, now that we're going to commit to that one atom, we're going to draw the rest of your structure the way you did it. The T-butyl group at this carbon is on a wedge. That means above the ring. So above the ring at this carbon is equatorial up. One, two, three, four. On the other side, I'm going to put a chlorine over here. It is also on a wedge. At this carbon, the up position is axial up or equatorial up. This is axial up, so I'm going to put a chlorine up here. My T-butyl group is equatorial. My chlorine group is axial. You with me so far? Now, if you did not draw this exact structure, that doesn't mean you're wrong, but you do need to make sure they're 4 carbons away. So if you put one here, 1, 2, 3, 4, the other one would go here. If you put one here, 1, 2, 3, 4, the other one would go there. You need that relationship to work out, right? You can't turn 1, 4 into 1, 2, or 1, 3. But there's lots of ways that you can draw these on here. So this is just one way, which is what makes me a little hesitant for working these examples out. But by the way, this example I just had for you, where I gave you a thing, said draw 2 chair forms, label them axial equatorial, circle the more stable chair form. Kind of feels like an ABC question you're going to see on an exam or a quiz or both. Okay, so the T-butyl group over here was equatorial up. The T-butyl group is now here what? Axial up. Kind of waving hi to you, right? It's like, hey. 1, 2, 3, 4 on the other side. I had a chlorine that was axial up. Is the chlorine still up here? And what? Equatorial up. Okay, now the thing that I think I saw a couple of you flipping through your pages where you were like, who's worse? We didn't say anything about chlorine. And why didn't I say anything about chlorine? Because I'm mean and my heart is 2 sizes too small. No, I didn't say anything about chlorine because there are lots and lots and lots of groups you can put on cyclohexane, and I don't intend for you to memorize all of them. But let's just think about this. Chlorine is a big atom, right? It is 1 shell of electrons larger than a carbon. So if a carbon's this big, a chlorine's this big. So it's a bigger atom, no doubt. T-butyl group, though, looks suspiciously small, but it's big. It's a carbon that has carbons that have hydrogens attached to it. Oops. So I know I'm not supposed to. Yeah, that helps. No, stop it. I know I'm not supposed to make Harry Potter references because no one knows what Harry Potter is anymore, but I'm making a Harry Potter reference, darn it. In Harry Potter, which is this book about a young boy who's a wizard and learns how to become a wizard going to school. You should all go see it. It's great. There is this tree called the Whomping Willow. And the Whomping Willow is this mean old willow tree that's on the campus grounds. And if anybody gets near it, the Whomping Willow is like, wow, and just whaps it out of the way, right? There's a cool scene where it beats up an old Studebaker. T-butyl groups are the Whomping Willows of organic chemistry. It is a carbon that has branches, and it's spinning and turning, and it is just like, come at me, bro, whack, and it's hitting everything away. It takes up a bunch of space. Putting a T-butyl group into an axial position is like walking up to the Whomping Willow. Didn't work out well for the Weasleys and the Potters of the world. It doesn't work out well for this axial position. So putting my much larger group, my T-butyl group, in an equatorial position is the most stable conformer. There is nothing in the world. There are a few things in the world bigger than a T-butyl group because there's no way to get it out of the way. It's 3-dimensional and 3-dimensional and 3-dimensional. So it is literally a tree. And you can't just be like, hey, tree, can you like just turn your branches and get out of the way this way versus chlorine's a big atom, but it's a sphere, right? So it's not taking nearly as much space. Questions about drawing dye-substituted cyclohexanes? Or Harry Potter? Or why you should all be into Harry Potter, because they built a whole world for this and you're missing out if you don't know what's going on. Go watch Harry Potter, read the books, and then go to Harry Potter world because it's magical. Caleb.
People name this, like cis dash one dash fluoro dash four dash butyl cyclohexane.
Cis 1 T-butyl would get this one because it's but it's butyl B. 1 T-butyl 4 chloro, sorry, cis. Because I know what you guys are going to say. Careful. Or you should say that. Cis 1 T-butyl 4 chloro cyclohexane. Be the name of that molecule.
How would you do, say like you did one fluoro and then four butyl?
Then they would just be out of order, right? Because you're putting C before B. And A, B, C, D, E, F, G.
Not the T.
Yeah, so that's, some of these are annoying. A lot of prefixes, most of the prefixes we don't count. My, di, tri, tetra, tert, sec, we don't count any of those. And I wish I could say we don't count any prefixes, but for whatever reason, we count iso. So if you have isopropyl, the I counts, which is so annoying because otherwise you'd just be like, ignore all of it, right? But we had to throw in one exception. Everybody see a question coming your way? You're all going to get it right. The first thing you're going to do is draw me 2 clean chair forms. So that's going to get you a bunch of points. Then you're going to label those chairs with the groups. Then you're going to add labels to those groups, axial or equatorial. Then you're going to do some mental math of who's bigger. If I can put my bigger group in an equatorial position, that is good math. Circle that one. Sometimes they'll be the same. Often they will be different. You guys look like you really love cyclohexanes. And the reason that people hate cyclohexanes so much is it's a 3-dimensional object that we're trying to draw on 2 dimensions, and our brains start to break when we start to think 3-dimensionally like that. Well, I have a chapter for you. Chapter 5 is all about this. A fair warning to those of you who drive in a new place and are utterly lost 10 years later. So if you showed up to Tulsa and you drove somewhere once, you wouldn't know where you're going because you're new to Tulsa. If you lived in Tulsa your whole life and you still have to use Google Maps to go around our square mile grid system, you're very talented at other things, but spatial reckoning is not one of those things. If you find yourself getting lost pretty often, chapter 5 is not going to be fun for you. You're going to need to put in more work. If you are the sort of person where you can drive somewhere once and you're like, I own this place. I can go here wherever I want now. No map. Then you probably have a better spatial recognition. You better recognize landmarks and know how to place yourself in a 3-dimensional map. This will come easier for you, but you might still need to work at it. Chapter 5 is about something we call stereochemistry. And specifically, we're going to focus on stereochemistry at tetrahedral centers. Stereochemistry is a branch of chemistry concerned with the 3-dimensional arrangement of atoms. Stereo here means, bless you, in a similar way that you see in stereo. If you were to close one, or maybe you guys have done this. Anybody been to the eye doctor and they do this thing where they like move their fingers back and forth? I've not actually ever been to an eye doctor, so I've only had this described to me, but because I have a whole bunch of stuff wrong with me, but I have really good vision for now. It's gonna go away really soon. But they do this thing where they're like, they move their fingers back and forth and they're like, when do my fingers cross? Tell me. And you're like, stop trying to hypnotize me. If you try this right now, drop your pins, give it a shot. When you look at your two fingers, move your fingers back and forth. Can you identify when your fingers cross each other's paths? Pretty well, right? Close an eye. Do it again. Can you still do it? Like freeze your fingers when you think they cross each other's path. Open your eyes and check your work. You're probably not as good as when you have two eyes on it. We see in stereo. What that means is we can perceive the three-dimensional orientation of objects because we see what's called parallax. We view from one side and from the other side, and our eyes compare that image to say, well, it looks like it's here on one eye, it looks like it's here on the other eye, so I can three-dimensionally place that object. We see in stereo. Stereo refers to our ability to view the world in 3 dimensions. We're not watching movie screens. I know that Marguerite is closer to me and C is farther away from me. If I had one eye closed, I could probably still tell. Otherwise, we'd have like relatively small and big people. But I'm making more guesses by looking at a one eye. That applies to chemistry as well. There's a 3-dimensional nature to chemistry that we have to account for. So if I have a carbon with tetrahedral centers with 4 different groups attached to it, so that would be a carbon, hydrogen, let's do it this way, X, Y, and Z. So the hydrogen, carbon, and Z are all in the plane of the page or in the plane of the screen. If this molecule looks into a mirror, so that's my little 3-dimensional mirror, the mirror image that this molecule is going to see looks like this. It'll have an X in the back. It'll have a Y coming out of the page, and it's going to have a Z, but it's going to be facing back the other way. These 2 molecules are mirror image molecules. Here's the complication. These 2 molecules look identical to each other, right? It's got an X, a Y, a Z, colors are all the same. X is on a dash, Y is on a wedge, hydrogen's in the plane. This is the same molecule, right? That I just drew twice. Well, it's not. What I'm going to do is pick up this molecule and I'm going to grab it by the hydrogen and I'm going to spin it like a top. So what's going to happen is I'm the carbon, my head's the hydrogen, I have a Z, blue on this side. And I'm going to grab my Y. So I have a Z facing this way. I'm going to pick myself up like a top, and I'm going to spin myself around so that the hydrogen's still facing up. So now my Z is over here. When I do that, this molecule is going to have a Z over here. One more time. This molecule, Z is over here. It's picked up by the hydrogen. I'm going to spin myself around. So now I have carbon, hydrogen, Z's over here. With me? What's going to happen to that Y? The Y was on a wedge, green. So pick myself up and spin myself around. Now where's the Y? On a dash. The Y went from a wedge to a dash. Same thing happens with the X, and I'm out of time, but I'll do it real quick. I don't have a red pen. Same thing happens with an X, right? The X was on a dash, it spins around. It's going to be now on a wedge. If I try and superimpose X, Y, and Z and the hydrogen between these 2 molecules, they won't fit. These 2 molecules are what we call enantiomers. Enantiomers are non-superimposable mirror image molecules. And I'm sorry, I'm a minute over, but one last thing, because I think this is important to drive it home. You have a pair of model kits in your hands. If you put your hands next to each other, your left hand and your right hand mirror one another. When my left hand looks in the mirror, it sees my right hand. Try and make your left hand be your right hand. Like, try and put them on top of each other to make the hands line up. You can't. I cannot superimpose my left hand on my right hand. The best I can do is kind of this awkward turtle thing, but it's going to be back to back or palm to palm, but I can't make my left hand be my right hand. My hands are enantiomers. They are mirror image molecules, mirror image objects that cannot be superimposed. There is going to be a left and a right hand of molecules that we look at all through chapter 5, R and S. We'll pick up with that and the topic of chirality starting on Monday. Have a wonderful weekend.